Okay, so good evening, everyone. So today we're going to talk about variational autoencoder. You can view it as a variant, a much more modern variant for the autoencoder architecture we mentioned in last lectures. And there we know that the vanilla autoencoder, the purpose is trying to what? Trying to reconstruct itself. You try to copy the input to the output. You try to learn the identity mapping. And by setting your objective to be an identity function, you may learn some very useful feature, very efficient representation of your dataset, right? And variational autoencoder is kind of adding some probabilistic spin into this architecture. And by adding this probabilistic point of view into this architecture, we can focus more on the data distribution. And this approach is invented in 6 years ago by Max Wedding. Max Wedding was a physicist in before. He was the kind of the last one of the best PhD students from Tahoft. And he did quantum gravitational studies in before, and then he turned into the machine learning community. Now he is the leading figure in Netherlands, yes. And this is also telling us a lot of modern machine learning techniques has very close relationship to physics studies. Okay, so now let's start with the discriminative and generative basic machine learning tasks. So in before, we talked a lot about the supervised learning approach, right? So in last lecture, I also mentioned to you that that's supervised learning. Basically, the goal is trying to do predictions. You try to find some mapping function, like here. You want to find a mapping from your input X to some output. This can be a target or can be some classes, identity, or some regression observables. And then based on the learned mapping function, you can do prediction for future. Once you have some unseen, some new coming X, then you will know what the Y should be associated to this X. Or in a probabilistic point of view, you can say, this is trying to learn a conditional probability, right? We have some parameterized model, yeah, we call it P fit of Y given X. We try to tune the parameter theta to let it approach a conditional probability. This P of Y given X. X is your input, Y is the target. So this is all about discriminative learning. And there's also another very popular learning paradigm or task. This is generative model. And there, the main purpose or the main focus is trying to get a deeper understanding of the data structure. You want to represent the data structure. You want to represent the data distribution, some underlying the mechanism for generating this data set we collected, right? And much more popularly, we want to learn what? We want to learn the joint probability distribution compared to this conditional probability. And actually, once you have the knowledge about this joint probability distribution, you can also get the knowledge about the conditional probability, right? You just apply the Bayes rule. You know that this conditional probability can be derived from this joint probability. You just divide it by the marginal likelihood, right? If I write it here, this equals what? The joint probability divided by this marginal likelihood. So people call this P of X to be the marginal likelihood because this P of X is what? Oh, sorry. And this equals to integration of the joint probability over dy, right? That's why people also call it marginal likelihood, marginalize the joint probability over the conditional target. Or in machine learning community, people also call this P of X to be evidence This is somehow the observation we have. This is the visible observable we can get access in. Okay. And yeah, so now basically from last week, we started this generative modeling. And one of the very popular quotes from a physicist is Feynman. He said, he wrote in the blackboard that what I cannot create, I do not understand. This is basically one motivation why we care such kind of generative ability. You want your machine to have the ability to imagine, or let's say to have the creative ability. You want to make some new examples. You want to let your machine to be able to generate you or to synthesize you some new examples. And these new examples might look like the training data that you have. So they share the same statistics, but they are not exactly the same. So you have the diversity inside your generative model. And what variational autoencoder is doing is a generative modeling, but it's using some kind of latent variable. So what's happening here? Why there is no, wait a minute. Okay, maybe we use this one. Good. So we will use latent variable model. So soon I will tell you what the latent variable model means. First, let's clear up the problem set here. So a very general problem set for generative model is that we want to model our observations underlying but unknown distribution function, right? So I guess I wrote this in one of our lectures in before when we try to introduce the maximum likelihood, right? So we assume all of our observations must have some underlying but unknown distributions. This we can call it the P data of X, right? And what generative modeling is trying to do is to understand this data, including its inherent structure, its properties, or some of the useful features that can represent the data much more efficiently, right? And another purpose is you want to have the ability to sample according to the same, this unknown data distribution, right? So usually we assume the observation data set have this IID properties, this identically independent distributed according to some underlying distribution function, right? So this is just to remind you again. So we assume our training data set fulfills such kind of IID properties according to a data distribution function. And we want to use some model, and this model will be including some parameters. So this is a parametric model to approach this data distribution function. You want to tune this model parameter theta to let your model to capture this underlying data distribution, right? This is our problem set for a very general generative model. And what supervised learning is doing is to modify this distribution function to be only some conditional distribution function, right? Like P of y given x, not focusing on the observation here, but we cares about some content, this y. So what kind of information, what kind of abstract content is contained in this x? So what appears here? Oh, that's very strange. Okay. I don't know what's this, why this blank, this white blank areas comes out suddenly. Okay, so anyhow, variational autoencoder will apply the latent variable modeling. So what latent variable modeling means? So basically, we assume for any visible observables, there must be some hidden variables being associated. And these hidden variables, so you can call it the latent variables, that can much more efficiently represent your original data set. And actually, this kind of latent variable idea is quite popular in physics as well. And in general, these latent or hidden variables just a very powerful way to encode some sophisticated correlations. Like suppose our X might be some pictures or might be some field configurations or whatever your system representations. There you have a lot of very sophisticated correlations like here, right? This is a three-dimensional space. And we know that this kind of visible, very complicated correlations inside your visible world can have some very efficient way, some much lower dimensional space to represent it. Like here, you can flatten this visible world into a two-dimensional manifold. And this two-dimensional vectors, you can call it a latent variable. And this idea is very similar to integrating out some variables, some hidden variables to induce these very complex correlations in physics, right? Like when we consider some free electrons living in the lattice, you can integrate out the photons to give rise to the very high order electron-electron interactions. So that's the same idea. Or we know that in gauge theory, so in the Wilson renormalization group paradigm, we know that all electric the effective field theories, they can also be thought of as just arriving from some field theories that integrate all some high energy degree of freedom. And this high energy degree of freedom, you can think of this somehow the latent variable we're talking about here. And in practice, this has some much more evidence that first, this can be the imagination. Like if I want you to draw me a picture, you will first think what? You will first think what content I want to draw, right? I want to plot. This is somehow the imagination in your brain. And or I want you to write an article. So you will first think about, so what's the thing? What's the topic I want to write, right? So this is the very abstract degree of freedom to represent your final object, right? Or this can be some outline or class ID or some foundation stuff. So anyhow, this is the imagination. And in later, we will use the example of the handwritten digit generation. So you want to generate some handwritten digits, like it's a number 2, a number 3, number 4, is some handwritten digit. And if you do the same task, the first thing you will think about is what? So which digit I want to write, right? So this digit identity is also one kind of the latent variable here, okay? The other evidence that latent variable modeling can be very useful is this manifold disentangling. Yeah, this basically is saying that all the real world objects, whatever the pictures or sound, audio, video, or some even the field configurations, they are only seemingly high dimensional. Like for this handwritten digit, if you use the MNIST dataset, the dimensionality is what? Is 28 by 28. It's a high dimensional space, right? But it's only seemingly such high dimensional space for each data point of this handwritten digit. A lot of the pixels inside this matrix is what? It's just 0. And in machine learning community, people believe that this seemingly high dimensional space object, they have a much lower dimensional embedding. So basically, you assume all the real content, all the efficient representations of this object is kind of a low dimensional embedding, like here, like this picture. The most important information, most informative content is just a low dimensional embedding inside this high dimensional, this 3-dimensional space, right? So here, this is a 2D manifold embedded in this 3D real world. And so we can use this latent variable model trying to disentangle or trying to flatten this manifold. And once we have the access into this manifold space, this hidden variable space, you can let your learning algorithm to be much more easily, like you just use some linear algorithm, you already can do the job. But here, if you want to have some, let's say, some interpolation in this 3D world, from this object to this object, if you do a linear combination, this gives you some nonsense object. You see, the cross point might be the average over 2 objects lies in this real world curve. The average is outside of this curve already, right? Once you have the ability to flatten it, you can do the interpolation much easily, just a linear combination that can suffice. Then another motivation to use latent variable modeling is this transformation, the cumulative distribution function. That in mathematics or in computational physics, we know this already, that between any two distribution functions, once their dimensionality is the same, there must exist some transformation function to connect these two distribution functions, right? Actually, in probabilistic theory, this can be precisely proved. Whatever your distribution function looks like, it might be multimodal or very, very complicated curve. Once the dimensionality of these two distribution functions are the same, you can transform from one distribution function to another one. And the key idea is you just apply the cumulative distribution function of one of the probability. You just apply this CDF, the inverse CDF on this probability. You will get this, right? And maybe I can tell you one example. So let's do this exercise for you. So suppose you know how to randomly generate some variables. You have a random generator, but this random generator only give you a uniform distributed variables. So you have this U can be randomly generated from a uniform distribution between 0 and 1. So I ask you one question. Based on this random generator, how can you generate some variables according to such a distribution function? This, let's call this f equals to exponential function, yeah, e2 minus lambda x. How do you do that exercise? So from computational physics, or once you have some knowledge about Monte Carlo sampling, you know the way to do it is calculate the CDF, right? So this f is our PDF, right? This is our probability density function. Once you want to generate some variables according to this PDF, based on some already known random generator, what you are doing is first calculate the cumulative distribution function, right? So you just calculate the integration from minus infinite to some x of this, right? So you do this integration. The result, if I remember correctly, it will be the same function format, just taking the negative. And now you're just using the CDF inverse, just inverting this function. So basically you solve this function, solve for x, right? And you will get the result. This will give you the generator. Yeah, that's, you can call it CDF inverse u. This equals maybe, yeah, minus log. Yeah, because 1 minus y, 1 minus y. If y is taken from this randomly generated stuff, and yeah, the log, because you want to inverse this exponential. So that might be the result. We can actually test it here. Let's have an example. So let's randomly generate some stuff. Let's call it U, right? So in NumPy, you already have this random generator. That's random.random. And the argument, you can specify how many events you want to generate. Let's specify, let's say 5,000. So U would be a randomly generated vector according to this uniform distribution. So the length would be 5,000. So now let's turn this U to be an exponentially distributed random vector. Just apply the CDF we calculated is what? Minus log 1 minus U, right? Okay, let's plot it. Let's first plot U. Let's say beans random uniform. Yeah. Yeah, it looks like a random, right? Now let's plot the E. Hopefully this is exponential. Yeah, that's right, right? So this kind of idea is actually very general. Here we just apply the same kind of idea that we believe the visible world must have some hidden world to be connected using some transformation function. So we will apply the latent variable model to take advantage of these three aspects of the real world. Now, why? That's very strange. I thought once I have written something there, it will give me the blank. Good. Okay, so now let's apply this latent variable model. And what a general latent variable model could be written as? This is the form, right? So we have some latent variable z, and based on the z, we try to generate, or we try to plot, we try to create some visible world dataset x. So you always first decide what's the latent variable you want to have, and from there you do your creation job, you do your generation job. So this is p of z times p of x given z. And this integration means you need to search over the entire latent world to have your final generative job done, right? So in general, one generative model based on the latent variable modeling can be written in this form. This is just what? This is just the integration rule for the probability theory, right? Just there, we inserted some conditional probability, this P of x given z. This can be your generative model with condition on some latent variable z. This z might be the digit identity. I don't know why there is such stuff. Why there's always this. Okay, that's very strange. Sorry for that. Okay, so in machine learning community, people also call this kind of generative model to be a directed graphic model. The graphic model, you can plot it as here. Basically, you first have some access into sampling a z, yeah? And people also call this is your prior knowledge or your prior imagination inside your brain. And based from this prior knowledge or based on this prior latent world sampling, you do your generative job using this p theta of x given z. So from here to here, this solid line is just do the job of px given z with a parameter theta, okay? Now the question is how to choose or how to assign this latent variable, how to let your latent world to capture some information about the visible world x. Like for the handwritten digit case, we know that this latent variables can be the digit identity, like this is a number 2 or number 3, or this can be your handwritten style, like You write it in this way, or you write it in that fashion. Or this can be the stroke, the width of your lines, right? You can write it in a very thick fashion or in a very thin fashion, or different angles. You write it always not vertical, but in some specific direction. You have a lot of abstract information that can control your generation, right? But how to choose that? This is quite complicated. And also, we know that between different factors inside this latent world, there are entanglement. They are internally correlated. Like once you write a digit very fast, maybe you will result in a very angled written, and also the width of your lines will be very thin, right? This is somehow correlated. So to manually represent these very complicated dependencies of this latent variable components, this is basically impossible. And for different data sets, you will have a different latent world assignment, right? So what variational autoencoder is doing is trying to avoid all this manually assignment for latent variable information and also their internal dependencies. Avoid it, but how to do that? It's just assuming the latent Z can be just sampled from a very simple Gaussian distribution. It can be a multivariate. So the Z, you can be a high dimensional case, no problem. But we assume it can start from a very simple Gaussian distribution function, independent, multivariate, Gaussian, normal Gaussian. And again, one key idea that why this kind of assumption can work in the end is because we know that any d-dimensional distributions can be generated by a d-normal distribution function going through some mapping transformation. This, in the one-dimensional case, this is just what? Just the inverse CDF, the inverse cumulative distribution function we already shown there, right? And once our task, once our generative job needs some complicated latent variable representations, even though our starting point is not that complicated, we know that there exist some mapping functions, right? And usually from the Z to X, you will use some neural network. At least here in our variational autoencode approach, we will use neural network to represent the mapping from Z to X. We use a multi-layer neural network. So you can imagine the very first or the very first several layers of the neural network can do this mapping, can help you to transform this very simple Gaussian distribution function to the latent variables that can really capture the efficient information about your original world, right? And then they use the later layers to map from the Z, from the latent variables to the visible world X, right? So you can decompose this kind of generative model in two steps. First, we start from a very simple Gaussian prior. This might be not the very reasonable latent world. So you can use the neural network, the first several layers, to learn this mapping function. Yeah, it will to help you to transform this very simple Gaussian noise or the Gaussian prior knowledge into the real Z. Let's call it Z tilde. This real latent world. This might be the stuff like the digit identity, number one, number two, also the style, your handwritten style. You have different format to write it, or you have different angle. All this very abstract, the semantic information there, right? And then the network, yeah, this mapping network will use the later layers to learn how to map from this real latent world to the X world, to the handwritten digit world, okay? So this is possible. Once there exists such kind of reasonable latent world, you don't need to worry if it exists or how to get there. Once there is such kind of stuff can help your algorithm to learn to accurately generate your X, the model, by training, we can let the model to capture this way, okay? Okay. Okay, again, that's Basically, I cannot write here. Why? By the way, once you have questions, you just interrupt me. What happened? Let me reopen it. Okay. So now we already have our formula for the generative model. That's here, right? This integration. And we also assumed this prior P of Z to be a what? To be a simple multivariate independent Gaussian distribution, right? So now how to do our generative training, how to learn the model, how to tune this model parameter theta. So what's the principle? So a very general, a very basic principle is what? Is the maximum likelihood estimation. So we already talked about it several times, right? So basically the idea is we try to let the observations to be much more likely under our generative model, right? So we try to apply the theorem that what exists is reasonable, right? 存在即真理. We want our model to have a large chance to generate the already collected training data. And the likelihood, as we also said, to prevent the numerical underflow problem, usually we take a log there. And by taking the log, we can convert the product into a summation of the log, right? And why this is product? Do you still remember? The likelihood on our training set X, this capital X is what? Is our training set, the series of data points, right? Because we assumed our training set is IID, it's independently distributed according to a data distribution function. So we can convert this P theta of X into a product of each data point, their likelihood, right? Then we take the log, we can convert this log likelihood of the whole training data set to be the summation of the log likelihood of each singular data point. And now what maximum likelihood estimation will do is asserting that the optimal model parameter is the one which can maximize the log likelihood, right? And because inserting a constant will not influence the result of this argmax operation, so we can insert 1 over n here. N is our number of data points we have in the training set. And this is what? This is the expectation of this log likelihood on the weight distribution function. This is P data log P theta X. This is just this expectation, right? Because to evaluate an expectation, once you have some examples, you can estimate it using this summation, right? And here, precisely speaking, this is not the P data of X, but what? But an empirical data distribution function. So you can add a tilde here. This is using the already existed observation. You use all the collection you have to construct an empirical distribution function. So usually you can write it as a summation of a Dirac distribution function, right? This periodical data distribution function is just the summation of x minus xi. You have all different observations you got, right? Okay, so now we also know the principle here. The principle is maximizing this log likelihood. Can we do that now? So you may think, now you know the principle. You also have the data observations, and you have a parameterized model P theta. So you just calculate this log likelihood, right? You take the derivative of it with respect to the theta, and you apply the gradient ascent, right? This is you try to increase the log likelihood, the job is done. Why we need to take this lecture here? Basically, there is difficulty. Where is the difficulty? Here, we see that for each singular data point here, the log likelihood is a what? It's an integration, right? Because we said our generative model is a latent variable modeling based. So there we need to integrate over the entire prior space, the entire latent world, PZ. So you need to do this integration first. And usually our latent world is not a very simple prior world. It can have multiple variables. It can be high dimensional. So this is a multi-dimensional integration. So to do this integration, this is not very simple. And this is actually intractable. So what you can do when you look at this integration with the log. So this is a log integration. By the way, mathematically, this log integration is equivalent to do a log of summation, right? And quite often, or in whatever physics or in machine learning community, people do not like this log of summation stuff. Why? Because it's not possible to differentiate it. If you want to calculate the gradient, or if you want to apply some optimization algorithm, you first need to calculate the derivative of this formula with respect to a model parameter. But here, a log of summation, how to do this differentiation job? We know summation of log, this is fine, but log of summation, we don't know how to do that, right? And actually in physics, we have a lot of integration tasks. Usually what we will first try is what? A very straightforward try is Monte Carlo exampling, right? So let's do that. You just what? You just example a lot of z according to this P of z, right? And you throw your example z into this generative model, this P of x given z, and you sum them together. So this can be kind of an estimation for your P theta of x, right? This marginal likelihood. But how many z you would need once you want to have kind of a reasonable, or let's say you want to have an accurate estimation for this P theta of x, how many z you would need? You will need millions of z, a lot of z. Why? Because for a randomly generated z, so what's the value of this P theta of x given z? What's the expectation? So what's P theta of x given z for a z randomly generated from your prior distribution? By the way, this x is a given x. Let's say it might be a handwritten digit 2, looks like something. Yeah, let's randomly write something handwritten digit. Let's we just focusing on what's our model's probability on this specific x. So this x is a fixed some independent fixed input data point. And for that fixed input, what's this value? This value is basically 0, right? Otherwise, you are just so lucky. By randomly generating a z, you throw this z into your P theta of x given z, you get something very likely to some already existed observation. This is impossible. This is just very similar to you let a wild monkey to type you an article to be publishable in PRL. This is impossible, right? So how to solve this problem? In this case, we see that in this joking example, this is basically let a wild animal to type you some meaningful article out. Why this is impossible? Because this is the wild animals, right? The wild monkeys, they have no knowledge. So the way to do it is you need to educate them. You need to teach them how to type out something meaningful, right? Shit, why again? Why again? So how to do that? You educate it. educate the monkeys on which kind of information? You educated what kind of typing or what kind of latent variable can be related to this specific X, right? Like you want you want this animal to type you a banana word out. So you need to teach it what kind of typing can result in a banana in the end, right? So this is basically to have some knowledge about what values of Z have been produced X, right? And in the mathematical format of this problem is asking the question, can we change the order? Can we change this log of summation to be a summation of log, right? So how to do that? The way is importance sampling, right? In importance sampling, so we know that to improve this kind of expectation evaluation, we can resort to the importance sampling. It's saying that when we need to evaluate an expectation, yeah, with respect to some original, yeah, this is the original distribution function, we need to do the sampling. People usually call this is what? This is the nominal distribution function. What importance sampling allowed us to do is we can insert or we can make another proposal distribution function, different from this a nominal distribution function. And you just sample according to this proposed distribution function. And then you weigh your sampling by this factor, right? Basically, this is the same thing. You just insert QZ over QZ. This is identity. And you do your integration or you do your summation according to this distribution function. This is important sampling. And here, if you really want to change the order of this formula, we need to apply the Jason's inequality, right? So what Jason's inequality means? Once your function is convex, yeah, we know for convex function, the mean of your function is always larger or equal to the function's mean, right? And here, this log is convex. Oh no, sorry, log function is actually, precisely speaking, this is a concave, right? Because log looks like here. I don't dare to write here. I can write maybe here. Yeah. Okay, good. Right here. So we know the log function looks like this, right? So for any 2 point on this function, the mean of the function, because this is concave is inversely, right? For concave functions, the mean of any 2 functions that's here, right? You do the summation can be average or can be any linear combination, will always be smaller or equal to function of this mean, right? This solid point is larger or equal to this cross point here, right? That's what Jason's inequality telling us. Okay, now for this importance sampling procedure here, so what kind of Q of Z you want to impose here? So which is the optimal proposal function you could expect? If you want to have a very efficient sampling, a very good sampling, this proposal distribution function should at least proportional to what? Proportional to your nominal distribution function times the function you're trying to evaluate the expectation, right? So the optimal Q of Z should proportional to P of Z times this Px given Z. So what's this? I hope this can remind you to think about the Bayes theorem. So this is the prior times the likelihood. This is what? If you divide it by a constant, the P of X, this evidence or this marginal likelihood, this is just the posterior distribution function, right? So this tells us the optimal proposal distribution function is what? It's just the posterior distribution function here. And actually, once you insert this posterior distribution function, you replace it to be the Q of Z. This is just exactly calculating the log p theta, right? Because we know that log p theta, yeah, it equals to this, right? If you insert the p, if you insert the posterior p z given x, you insert this ratio, right? Here, this is a numerator. Here, this is a denominator. And you can change the order of the integration and log. Because why? Because this is p theta of x. If you apply the Bayesian theorem, right? This is the, in the numerator, this is the joint distribution function. The joint distribution function divided by this posterior, this is what? This is p theta of x. Log p theta of x, this is a constant. Why? Because for a fixed x, p theta of x is not depending on the z. So you can extract this log p theta of x out, and then you integrate this posterior distribution function over z. This is because this is a normalized distribution function. In the end, it's exactly the log p theta of x. So basically, this is exactly equaling to each other. And in the mathematical format, this is just allowing you to change the order of the log and summation, but you can have an equality here once you are using this posterior distribution function here. Okay. I hope this can help you understand a little bit more that the posterior distribution function here is very important when we want to have some estimation on the marginal log likelihood, because the posterior distribution function encodes all the knowledge about the mapping from the X, from the original world to the latent world. It's basically the knowledge that we can teach the animals to type out something meaningful, right? That's where the knowledge are encoded. It's in the posterior distribution function. So once we have the access into the posterior distribution, we can much more efficiently evaluate this log likelihood, right? So now maybe we can think about if we can first evaluate this posterior distribution function. But just so unfortunately, still, we cannot evaluate this posterior distribution function, because to really evaluate this posterior distribution function, you still need to know something about the evidence, this p theta of x, right? This is just the Bayesian theorem. So the posterior equals the likelihood times prior divided by the evidence, right? And our starting point is to calculate the evidence, and the evidence will involve some high dimensional integration. So we try to use the importance sampling, and there we find the posterior knowledge is very important, but very unfortunately, we find that posterior calculation is also intractable just because of this denominator. Actually, this intractability is quite popular in physics as well. And in many statistical physics problems, we have the same, exactly the same format, just the denominator of for this p theta of x, we call it the partition function. And here, this joint distribution function is much usually, it's the Boltzmann factor, right? It can be the E2 minus E, epsilon, E2 minus energy function. And this is the partition function, right? Okay, so what variational autoencoder is trying to solve this problem is we do not directly calculate this posterior distribution function. This is also one idea from physics. In physics, when we try to solve this intractable problem, we have two different directions. One way is to using the Markov chain Monte Carlo to sample this, to make a lot of sample according to some Markov chain behavior stuff, right? And based on the Markov chain sampled stuff, we estimate the partition function and also the probability distribution, right? The other way is we use variational approach. So in variational approach, we propose some variational distribution function trying to approach this distribution function, this joint distribution function. We know that this joint distribution function is the normalization factor. This partition function is intractable. So we use a very easier proposed variational distribution function to approximate it. And the way to tune our variational distribution function is to calculate the variational free energy. And in physics, we know that there is the Gibbs inequality. The variational free energy we have is always an upper bound of the true free energy. So we just try to reduce our variational free energy. You do it in an iterative fashion, you can get what kind of parameterized way can really better approximate your physical distribution function, right? That's what we do in physics. Here is taking the same idea. So we also use some kind of variational distribution function to approximate this posterior distribution function, okay? So we propose a variational function, we call it q phi of z given x. So we have a parameter phi here. So this can be a lot of neural network weights or bias. And we want to tune this model parameters phi to let this variational distribution function to approach the ground truth posterior distribution function. So it need to be noted again here. This posterior distribution function has very close relation to our generative model. That's why there is this model parameter theta. Theta is what parameter? Theta is our generative model parameter, right? So for any kind of fixed generative model, there exists some underlying ground truth posterior distribution function. But we know this is intractable to calculate. So we use the variational inference to approximate it. We just propose a Q of phi to approach it by tuning a phi. So basically, we have two sets of model parameters. One is this theta. This is our generative model parameter. And the other is this phi. This is our reference. This is our variational inference model parameters. We try to get the connection from the real world X to the latent world Z, right? And tuning the model parameters, we can push this proposed variational distribution function to approach the ground truth posterior. Okay, now how to tune the parameters to let the Q to be close enough to the posterior. If you want to use some optimization algorithm, you need to have some objective, right? And in machine learning algorithm, the way to construct the objective is using the key error divergence. Maybe let me, sorry. Let me write it here. Good. So soon we will talk about this elbow stuff I wrote here. Yeah. As we said, we want to tune the model parameters phi to let it approach the ground truth posterior, right? And you see, our goal is trying to match two distribution functions. So the objective here is key error divergence. Key error divergence is kind of a measure of the similarity, or let's say the dissimilarity between two distribution functions. It's defined as the integration of P log P over Q, okay? By the way, maybe to remind you a little bit about the information theory we talked already in several lectures again before, that we know information is about what? Information I, or we can call it the self-information, is trying to quantify the degree of uncertainty, right? It's defined to be the log of some event's probability. And entropy is kind of calculating or estimating the average of the self-information under some probability distribution function, right? So this is entropy. So information is all about one single event, but entropy is about one kind of events, one class of events. This class of events is fulfilling some probability distribution function P of X. So you can calculate the entropy there. And key error divergence is kind of the relative entropy. So it's trying to provide you a distance between two different events. So how close these two different distribution functions are. And there are two very important properties for this key error divergence. So first, the key error divergence is always positive. It's larger or equal to 0, right? Is it obvious to you? By looking at this formula, this integration of P is positive. Actually, you can assign the Jason's inequality again. Let's see. So key error divergence based from this formula. Let's take the minus of that. This can be easily proved. So this equals P log Q over P, right? And we know that the log function is a concave function, right? So this is for concave summation, or the average of function is smaller or equal to log of the summation, right? So now you just change the order of this summation, the integration, and the log, the function. So it should be smaller or equal to, because this is concave function. And this is what? Log P times Q over P, because it's cancelled. We know Q is a normalized distribution function. So the integration over this Q is 1. So this is log 1, it's just 0. So this basically proves that the key error divergence is always positive. So this is the first property. The second property is that key error divergence is not exactly a distance. You can call it a measure or a divergence, but it's not a distance because it's not symmetric. It doesn't equal to Q and P. Because once we want to have a measure to be called distance, at least we want to have the symmetry property. Like you measure from A to B, it must equal to the result you measure from B to A, right? Otherwise, it's not a distance. So here, key error divergence is not a distance. So unfortunately, maybe that's also the reason why in the end, our algorithm based on the key error divergence will only give us some very blurry result, not the very clear looks result. That might be one of the reasons. So anyhow, here, this key error divergence can help providing an objective to pool one distribution function to match another one. So here, because we say our problem is we try to tune the model parameters phi to let Q to be very close to the real real posterior. So you just calculate the key error divergence between this Q phi and this P theta, right? This can be your objective. You just tune the model parameters of phi to reduce this key error divergence, right? This can let your optimization algorithm to be doable. Okay, so now let's calculate this key error divergence. We calculate Q phi z given x with the real posterior distribution function. By definition, this is what? This is integration over Q phi, yeah, times log Q phi minus log real posterior, right? And here for the posterior, this is always intractable. So we always use the Bayes theorem to transform it into something at least we have access. So we transform this to be what? To be the joint distribution function over p theta of x, right? This equals to this according to the Bayes theorem, right? Now we combine these two together. This is what? Log q phi minus log, sorry, p theta xz. And then this is plus integration q phi log p theta, right? In total, we have 1 term, 2 term, 3 terms, right? So what's the third term? This integration of q phi times log p theta. We need to write the argument clearly, then you will know the result. We say that log p theta of x has no dependence on the z. Sorry, I forgot to write the integration arguable. Yeah, that's dz. Yeah, here also dz. Because we say that this has no dependence on this dz. So this kind of a constant in this integration, you can extract this out, right? So once you extract it out, and because this q phi is a normalized distribution function, in the end, this is just log p theta of x, right? This is what? This is our marginal likelihood, the one we want to maximize, right? And let's rearrange it, the formula a little bit. That's q phi z given x log q phi minus log the joint distribution function, yeah, plus a constant, that's our marginal likelihood. That's the final expression. So first, let's go to the slides. I also have the results here. Yes, so that's what we derived, right? So people usually call the first two terms together elbow, or actually the minus negative elbow. So first you remember this written form, and if you replace it to be the L, yeah, to be the minus L actually, yeah. So you can shift this marginal log likelihood to the left, and you shift the key L divergence from the left side to the right. In the end, we will have this format, right? So the log p theta equals L plus dkl, the key L divergence between our proposal, our variational distribution function, and the ground truth posterior. So we started from here to calculate the key L divergence, and we arrived at something involved the log p theta and this L term, right? This L is just what? It's the first representation. And this in physics is also very popular. This is exactly the variational free energy. And usually, as we said already, this joint distribution function has an exponential format. You can write it to be E2 minus energy stuff. So taking the log is the energy part. And here, this integration of distribution times log distribution, this is the entropy. So energy plus entropy, this is the free energy, right? And why this is called evidence lower bounds? Because we say that the key L divergence is always larger or equal to 0. So this log probability is always large or equal to L, right? Based on this inequality, people call this expression, this L, the evidence lower bound, because the p theta of x in machine learning community, this is called evidence. or you can call it a variational or the variational lower bound. And this evidence lower bound is basically the cornerstone to drive the whole variational autoencoder to work. What variational autoencoder is doing is just maximizing this lower bound instead of this log likelihood, because we started to maximize this likelihood, right? Because our basic principle is maximizing the likelihood to let all the collected observation to be under our generative model. But we say that to calculate this marginal likelihood, we need to do a integration, the high dimensional integration. That integration is intractable. So we refer to the variational inference model, the variational approach. There we need to calculate the key error divergence between the two functions, the two distribution functions. So our goal is trying to reduce this key error divergence. And by deriving this key error divergence, we arrived at a formula here. So basically, this is relating the two goals together. Which two goals? The first goal is our very original goal. We try to maximize the log likelihood to tune our generative model parameter theta, right? And the second goal is we try to find which kind of variational distribution function can match the ground truth posterior much better. So we need to reduce this key error divergence. And we find this representation, this formula. So to maximize this elbow term, this L term, you can do the two optimization together, right? Maybe I plot here again for you. Oh, sorry. There is a famous plot, looks like this. This is the log p theta of x, yeah, and the height, yeah, the height is the log p theta of x. That's our model's log likelihood. And here, this is the key error divergence between the q phi and p theta, the true posterior. And this part is our elbow, the L stuff. L is a function of theta and phi together, right? So we have this formula that log p theta equals L plus the key error divergence, right? Q phi p theta. And we know that key error divergence is always large or equal to 0, so that's large or equal to L, right? Our two goals, one is increase this. So you want to increase this bound. You want to let it to be higher, as high as possible. And the other one is you try to reduce this gap, right? So to do this two job, you can use error. You can use this error, but we just maximize this error. It can kill the two birds together for you, right? That's how people say that one stone. This one stone is maximizing this elbow. It can kill the two birds together. The two birds is one is increasing the log likelihood for our generative model theta, and the other is trying to find the best variational distribution function to reduce the gap between the q phi and p theta. So in the end, our model parameters, including the generative model parameter theta and the variational inference model parameter phi, is just what? Just argmax theta and phi for this L term. You can call it Lagrangian if you want. This is our effective theory in the end. You just maximize this elbow, this evidence lower bound. Okay, do you have questions until now? I hope now it's clear to you that our job in the end are turning to just maximizing this elbow, because this can help us first increase the model's log likelihood, and second can help us to find a better variational distribution function to match the ground truth posterior, okay? And usually before, people start from this elbow expression, start from this one, yeah, the first one, and they do the EM procedure called expectation maximization procedure. It's kind of like the mean field theory. We know that in physics, the mean field theory have a very strong assumption that your latent variable can be factorized. Basically, you are ignoring all the internal correlations. This also reduces your model's expression ability. So what, compared to this very simple mean field theory, in variational autoencoder, they derived a different format for the elbow. So this is easy. So from the first line to the second line, you just what? You just insert again the Bayes theorem. You replace this joint probability distribution function to be the generative model times pz divided by p of z, right? No, sorry. You just replace this joint distribution function to be the product of this generative model and the p of z, right? From Bayes' theorem, we know that the joint distribution function equals p of x given z times p of z. Just replace this to be the two terms, and you combine the p of z terms with the last term, and by combining, you get another key error divergence term, right? Once we have this new format to represent the elbow, you can use neural network training to do the job. Why? Here, usually we assume this generative model in the end, you can have some very easily evaluated format, like you assume this p theta of x given z is a Gaussian distribution function. Then taking the log, you're actually calculating the Euclidean loss, right? So this is somehow the reconstruction loss. Like you throw in some latent code Z into a network and you get some deterministic output X, but you assume your model parameters to your model to be a Gaussian distribution function according to the output. This is very similar to our linear regression. So if you remember, when I talked about the linear regression, one or several slides, I talked about why we use the mean squared error to be the loss. Because we assume our model in the end is taking some Gaussian distribution function according to the deterministic mapping function from your input to the output, right? Z is our input, X is our output. Once you are using a neural network, the mapping, even though the mapping is deterministic, still you can assume some underlying probability. So usually for regression problem, we assume the underlying model distribution function to be a Gaussian. And this Gaussian distribution function will take the mean of the calculated mapping output, right? And we use this to be the mean, and we set some other variance parameters. Then we take the log of this probability. We arrive at the mean squared error. Here the same. So here, this is just what? A reconstruction error. So you're trying to let your generative model to give you some output that looks very similar, or let's say exactly similar to the data set inside your training set. And this term can be viewed as kind of a regularization term. It's trying to push this proposed variational distribution function to be very close to our prior setup for the Z, for the latent codes. As I said already, what's the P of Z? We assume this is a Gaussian distribution function. And in reality, this can be enough because we know that between any two D-dimensional distribution function, there must exist some transformation function that might be a very complicated CDF, the cumulative distribution function, to map the two together, right? So here, we use this key error divergence to let the Q phi, our proposed variational distribution function, to be very Gaussian-like stuff, right? That's why once we are using this kind of way to calculate our objective here is the elbow, then we have some kind of autoencoder structure. Here, this p theta of x given z, this is the decoder. You're trying to decoder from the latent world to the original data world X. And we have some model. It's parameterized with model parameter theta. And meanwhile, you have some encoder. This encoder is trying to do a recognition job, trying to do some inference that what kind of Z is related to your observation X, right? And you also want your encoder network structure or the mapping function here to be not very arbitrary stuff. You want it to be a Gaussian-like stuff. This is kind of a regularization. Okay. Now, let's model them. Let's really model them using the neural network, okay? As you said, for P of Z, we already have our model. We assume our prior, or let's say the source of imagination can be very simple. It's just a Gaussian, multivariate Gaussian distribution. And for the encoder, yeah, this is our encoder. This is our decoder. We want to use neural network. And again, as we said, neural network is only providing us some deterministic mapping, right? From input, you get some one-to-one mapping output. To really let the neural network to give us some probability stuff, you need to assign some underlying distribution function, right? So here we assign the encoder and decoder to be both Gaussian-like. This assumption is kind of for the sake of computation. You want to let your objective calculation to be analytical. In the end, you can really evaluate your loss function and you can calculate the gradient easily. That's just for this purpose. We assume this Gaussian distribution function here. Actually, you can also assume other different distribution function like Bernoulli distribution function. Once your original data world is binary variable, like you only cares one pixel have or not have some values, you can use Bernoulli distribution function. Or you can use some other very complicated like beta distribution function or Laplace distribution function, any kind of way. Here using normal Gaussian distribution function, we can easily calculate the loss. Soon you will see that. Okay, so for the encoder, we assume it's a Gaussian distribution function with the mean of f theta of z. So what's f theta of z? This is just what the neural network is trying to learn. We know that neural network in the end is just trying to fit a function, right? Just trying to learn a mapping function. And for the encoder, the input is z, the latent world stuff. You input a z, you get some output x. You call this function to be f theta of z. So we use this output to be the mean of a Gaussian distribution function. And you also introduce a variance term here. Yeah, this is a standard deviation. But you assume it's a diagonalized format. So you see that we only introduce a scalar number times an identity matrix. This is also for the simplicity of computational, because soon you will say, once you want to calculate the key error divergence, and you need to calculate the determinant of this variance matrix. And for a diagonalized matrix, you can easily calculate it. It's just the summation of it, right? Okay, that's the encoder part. Then for the decoder part, again, we are using a Gaussian distribution function. So we introduce a mean and a variance. There is a arrow here. This should be phi, okay? Both the mean and variance are sharing the parameters phi. That's why we call it Q phi of z given x. And for encoder, the parameters, all the model parameters, all different neural network weight bias are summarized in this theta. And for the decoder part, the parameters are encoded in this phi, okay? So neural network is only outputting us the parameters for some distribution function. And here we're taking the Gaussian. Now, once we replace these models into our objective, into our loss function. So you remember here, we have the loss function here, right? We use the second line. You insert the, for example, for the first term, we assume the encoder is a Gaussian distribution function, then taking the log, what's the result? It's the mean squared error, right? Again, it's kind of a reconstruction error, similar to the one we saw in autoencoder. And now if we insert the Gaussian distribution here and here, the key error divergence can have a closed form representation. I suppose you do this exercise by yourself. This can be your homework. That what's the key error divergence between two Gaussian distribution functions that can let you be a little bit familiar with this term. And once you do the exercise, you will find the key error divergence between our Q phi and P of Z is in the end is here. This is the trace of the variance matrix, and this is the mean. For scalar case, this is just the mean square. And key is the dimensionality of our latent word. So how many vectors, how many components you have for your latent code. And this is a log determinant. And as we said, to calculate the determinant of a matrix is not so easy. So to simplify the calculation, we usually assume our Gaussian distribution's variance to be diagonalized form. So this determinant can be just a summation of your diagonalized element, right? That's why we have this simplified version here. Okay, so now we have the loss function with two terms. One is this reconstruction error, one is this regularizer. Sounds like all the job are done, right? Now, if we throw the stuff into your calculation, we can construct the algorithm pipeline looks like here, right? You throw in our training data X into a decoder first, into an encoder first, right? This encoder is trying to map what kind of Z can be associated to the training data, to each specific training data. So you calculate the mean and the variance. And then you use this mean and variance to construct a Gaussian distribution function. From there, example a Z, example some different Z from this Q phi. So this is our Q phi of Z given X. You throw your example Z into your decoder. This is your generative model. So calculate the f of Z, right? And we use this f of Z to be a Gaussian distribution function's mean. So you can get your final output. And this blue rectangular is basically the loss function calculation. So from this part, we can calculate the reconstruction error, this mean squared error, right? This input X minus Fz, you calculate the Euclidean loss. And here, using this mean and variance, you can calculate the key error divergence. Combining these two, this is what? This is our elbow representation, right? So this forward pass, basically no problem. You just throw in X, calculate the Z, mean, variance, sample a new Z, you calculate the output, the reconstruction, no problem. But now to train the theta and the phi in these two networks, you need to use what? Backpropagation. You need to backpropagate the gradient. And here, this red color means this operation is not a normal operation. It's not a deterministic operation, right? This is a stochastic operation. And in mathematics, we basically don't know how to calculate the gradient for a stochastic operation. Like from here, if you want to backpropagate the gradient through this node to here, no way. We don't know how to do this job because this is a stochastic procedure, right? This is one of the difficulty in doing this variational inference for a long time. What variational autoencoder is introduced is a reparameterization trick. Basically, it's moving the stochastic part into the original input. Because we know for backpropagation, we only care the gradient of your loss function with respect to the intermediate model parameters. If you have some stochastic procedure in the original input, this doesn't matter because we do not care the partial loss over the partial original input. This is not our focus. So we we can use this reparameterization trick to kind of move the stochasticity into the input. How to do that? We see that the difficult part lies in sampling a latent z according to a Gaussian distribution function, right? And in mathematics, this is actually equivalent to first sample some random number, we call it epsilon, according to a standard distribution function, the standard Gaussian with 0 mean and unit variance. And then you do this linear combination. So you construct the z from this mean plus your variance times this randomness. This is equivalent, this two, right? Could you see this? So you first randomly generate something according to the Gaussian distribution function, and then you throw this randomness into a fixed mapping function. This fixed linear mapping function is just the mean plus the variance times this randomness. In the end, if you do the histogram for the z, these two are the same, right? So what VAE is using is just here. It's called reparameterization trick. So you can move the randomness into the initial input. You sample the epsilon from a standard Gaussian distribution function. And here, this part, this is deterministic. That's good because we need a deterministic mapping to do the back propagation job. And once you have the mean and variance calculated, you combine the initially randomness together, you will get a z. This is equivalent to sample z according to this Gaussian distribution function, right? And then you throw it into the decoder part. All the calculation through the pipeline here are deterministic, and you can calculate the gradient. You can have a closed form expression. Okay, so basically all above is the underlying mechanism for VAE. Do you have questions until now? If no, I can show you some result. So I'm not sure. Did you play around with the code about autoencoder I sent to you last week? If you played around with that, and if you plot, let's say for the handwritten digit, you set your latent space to be only two-dimensional keys, so you can plot the latent code for every handwritten digit, right? In the end, the latent space will looks like what? The latent space will basically looks like something. Some spot. So you have some gap between different digit identities. That's what autoencoder will result in for you. But for variational autoencoder, we also have some spot, yeah, so have some clustered stuff, but they are very close to each other. This is the function from the key error divergence. As you see, our objective function, besides the reconstruction error, we also have a key error divergence. This key error divergence is trying to let your encoder's output, let your latent space to be very Gaussian looks like, right? It's trying to shrink your latent space. So compared to autoencoder, compared to the vanilla autoencoder, in variational autoencoder, we introduced kind of attraction force besides the reconstruction error, right? This is very similar to the Van der Waals kind of interaction in physics, because the reconstruction error is trying to let your model to be able to distinguish each separate training data points. So it's kind of a repulsion force. And then the key error divergence is trying to let your latent space to have some shrinked properties. So in the end, this two forces work together. So you have kind of a balanced result. You will have this, still you have different clusters for each digit identity, but it's close to each other. It's shrinked into your center. And by looking at this latent space, it's very interesting that we can have a smooth manifold, right? And if you move around your latent space, you have kind of a continuous morphing. This morphing means using this trained autoencoder, this trained variational encoder, we just use the decoder part. You basically can have a generative model. So to let your generative model work, you just randomly sample some z according to your prior Gaussian distribution function. And you throw this randomly generated z into your decoder, you will have a generator. You can generate some new examples. And if you move your z like from here to here, let's say here this number is 0, and this number, I don't know, this number is what? This might be number 9. So from here to here, you will see you are generating number 0, 0, 0, 0 until here. There are a sudden kind of a phase transition. It will then generating you something looks like number 9, and then number 9, number 9, number 9, right? So that's what I mean. You can do the continuous morphing here. But on the original data space, this is impossible, because once in the pixel space, you want to do some linear combination, you're just overlapping two images together. It's not giving you some making sense, a reasonable digit. But on the latent space, you can do this linear combination, or you can do this morphing easily. And some more results, like here. So this is trying to demonstrate that morphing much more clearly. You just convert the latent space to the image space, but you generate your latent code on a grid, right? This varying the Z2. So suppose we only have two-dimensional latent space, and you vary the Z1, Z2 in the grid, and by varying each grid, you generate what's the handwritten digits looks like. In the end, you will have this kind of morphing. And this also can help you disentangle in different features, like here, in different directions, it might give you a different on-guard handwritten, right? So like this, both number 1, this is the on-guard number 1, but here, this is a vertical handwritten number 1. So you have kind of the control for different semantic stuff. And in physics, that might be like the order parameter value, or let's say that might be the energy, or you can generate different energies, field configurations, or some other physical parameters you care, right? So you can have a much more clear morphing. And if you apply this on some realistic image, like for people's face, so in the end, you can automatically let the algorithm to capture some useful or very interesting features, like from up to downstairs, this is what? Okay, some changing, but definitely from in the middle, there are something like the smile degree, right? Like here, this is smile, or the direction, which direction the face is looking at. You can also change this. So basically, some hidden features can be automatically disentangled. And this is why people
Sorry, can I ask a question? I'm sorry.
Yes.
Okay. A very nice question. So before we start the training, how can we know how many latent variables we need?
That's a good question. So as we said, using the VAE algorithm, we're always trying to avoid to manually set up what's the latent code to capture which information, right?
Mm-hmm.
You just randomly set some numbers first. But in principle, if you really want to capture the whole information of your training set, you need to calculate some kind of the intrinsic manifold dimensionality. For example, for the handwritten digit, we know that seemingly it's high dimensional, it's 784, 28 by 28, but there must exist some underlying let's say the lowest dimensional manifold to capture the whole information of the handwritten digit. That might be something, I don't know, several hundreds, 200 or 300. There are a lot, depending on how much information you want to decode out. But in practice, we do not care the whole information, because the whole information also includes some details, some noise, right? We only care, this is like the principal component analysis. So you can first just set maybe 2 or 3 dimensions. You get already some main features. This in physics might be your order parameter. That's only one information. And then if you care more information, just add more dimensions there. And the further dimensions might be the order correlation structure for you.
Okay,
This is
so
just,
okay,
yeah.
I know that. So I see. So the second question is related to that. So how can we measure how to say that the performance if we use the different number of the latent variables? I mean, if you use one or if you use two the latent variables, we can get some different performance, right? So how can we measure it? Use the
You
loss
mean how to
function?
compare,
Yeah, 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 yeah,
the
yeah,
performance? Okay,
yeah.
okay. For sure, once you have more dimensionalities in your latent space, you will get a much better performance. This performance is measured by the elbow, by that evidence rule bound loss. This will be much closer to the ground truth marginal likelihood.
Okay,
Once you
so
have
yeah,
higher, better for sure. But in practice, again, you do not care so much noise information.
So
Yeah,
so there must be some balance, right? So if we
some balance. That's right.
okay.
Yes. Also, depending on your purpose, like you cares about a generative model, you only want to generate some new stuff, and for the new generated stuff, you cares about some features like to the second moment or to the third moment of the distribution function. So we don't need a lot of latent information to encode the noise. Right?
I see. Thank you.
Welcome. But very good questions. Okay, so this picture is just trying to explain again that using this kind of algorithm, we can disentangle the manifold of our training data set. And maybe just look at the right upper corner. Our original data space, the manifolds might be very curved, right? That's why if you want to do a linear combination between 2 different data points, you will get something not making sense because it's already off. It's outside of your manifold already. So only once you have the access into the hidden space, into the latent space, we can kind of flatten or expand our data space manifold. And how to prove this is flattened? You just do a linear combination between 2 different data points. Yeah. So you insert 2 different numbers into your algorithm. You calculate what's the corresponding hidden code, and you do the linear combination of the hidden code in the hidden space. And you say if you throw this into your decoder and you decode back to some data to say if the generated data is promising, if it's really real looks like. If this is true, that means your manifold for your latent space is already flattened. And this is kind of proved already. So you can use your autoencoder to prove this easily. Like here, the original data space, the manifold, you can imagine it looks like this. And inside your autoencoder, if you do the linear regression on the first hidden layer, you get something that looks like this, right? And if you go to a deeper layer, you will get a much more promising linear combination. That means in the deeper layers of your algorithm, you are flatten it further, flatten the manifold further, right? And once you have this flattened manifold, you can do the arithmetic of different features on your data space, right? Okay, on the image is the same. Like you can even do the combination of 2 different people's image. It's kind of generating you something mixing the 2 different people's, right? Okay, so now let's summarize. Here, the variational autoencoder is a variational inference method. And the main job it's doing is just using the variational inference to approximate the posterior. And by derivation, we say that doing this can help killing 2 birds with 1 stone, right? One of the birds is we are trying to maximize the data, the model's log likelihood, right? The log p theta of x. And the other part is we're trying to find a better approximation for our posterior, right? So this in the end will arrive at an autoencoding setup. That's why we call it variational autoencoder, because we have an encoder part and a decoder part. And in reality, people always find that your output is kind of blurry. As I mentioned a little bit, this might be related to the principle we use. So we use the maximum likelihood estimation. And if you derive a little bit further, you will find this MLE, maximum likelihood estimation, is equivalent to minimize the key error divergence between our model, our generative model, and the periodic data distribution function. So maybe next lecture I will show you this. This is easy. So maybe that's the limitation reason. So we need some better metrics, not only this key error divergence. That's what GAN is doing. GAN introduced somehow a really, you can call it distance. Key error divergence is only a divergence, but not a mathematical distance. And what Jason Shannon divergence is doing is combine the two different measuring way of key error divergence. You can construct a symmetric distance. So that's what GAN did. And another thing is maybe we want to have a better evaluation of the likelihood, because here we are only using an approximation for the log likelihood. We're using the elbow evidence rule bound. Still, we do not have the explicit expression for likelihood. And once we want to have a further evaluation on likelihood, you need some flow-based models. Okay, that might be for future, for next lectures. Okay, so maybe I have no time. I just quickly show you the code part. I only show you the loss function part, maybe that will be enough. As we said, we need some sampling part, right? You want to have a sampled Z, the latent code, according to some Gaussian distribution function. And there we are using a reparameterization trick. So this is that the reparameterization trick, and also the sampling for Z. So first you calculate epsilon, the epsilon according to a standard Gaussian distribution function. Then you apply a fixed, a deterministic mapping, that's the mean plus this epsilon times a variance. And this mean and variance will be generated by some encoder neural network for you, right? And let's see the neural network part, yeah, here. So here, this is for handwritten digits. Input shape is 28 by 28, and we are setting the intermediate dimensionality to be some number. We just set some number. And here we force the very latent space to be only two-dimensional case. Yeah, that's the latent space equals 2. And this is an input. Here we're only using dense layer, the feed-forward neural network, very simple case, just to show you the idea. So this part, this 4 lines is constructing as the encoder, input here, the intermediate dense layer, and then the output. So as we said, the output, we need to have both the mean and the variance. So here we're taking the log variance. That's also for the purpose of simplifying the computation, because you saw that the formula for key divergence, you need to calculate the log determinant, and also you have an exponential of the truth, right? So that's why we take the log variance to be the output that can help avoiding the numerical underflow again. Then we do the sampling. So in Keras, if you want to apply some different functions, I mean, compared to the dense layer or convolutional layer, you can use lambda to wrap up any operation you want. The operation here we want to apply is sampling, right? The sampling we already defined in this function. We want to sample a Z according to the Gaussian distribution function with mean and the log variance here, right? So you can use lambda to do this sampling for you. And here, that's the decoder part in this for layers. So you throw the sampled Z into a dense layer, And in the end, you get your output. It's also a dense layer, right? And that's your decoder. You can combine them together. That's your variational autoencoder. But to specify the loss, you have two parts. First, a reconstruction loss. Yeah, here we're using binary cross entropy because here we're taking the handwritten digits. We only care about one pixel holding or not holding some finite number. Besides the reconstruction loss, we also have a key error divergence. So just apply that formula. Thanks that we assumed the P of Z and Q phi are both Gaussian, so we can have a closed form expression for key error divergence. So we can evaluate it here, right? So you combine the two loss together, that's giving you the total VAE loss function. You just compile it and you fit it. That's it. And after training, yeah, that's the stuff. That's the latent space, how the latent manifold looks like. Okay, and you can also make a grid generation. You vary the Z1 and Z2 on the grid and generate the data. You can have such kind of output. You see different numbers are already encoded from 0 to 1, 3, 4, yeah, every number basically. Okay, I will distribute all the codes and the slides to Xingyu. Xingyu can help distribute further. So do you still have questions? Some different questions? If no, maybe we can stop here.
Okay, thank you.
Okay, so thank you very much. Have a good night.